What do these things have in common? The answer is this. It's hard to imagine that thick, black crude oil is the source of so many familiar things. Not just fuel and oils for cars, planes and ships, but plastics, fibers, detergents, 1,001 items in the home, office and industry. How do so many things come from one rather unpleasant and smelly liquid? That's a difficult question, but it happens here. In this industrial complex, crude oil is broken down into its constituent parts, dozens of products from a single raw material. It wasn't always like this. When the world's first oil well spouted black gold in Pennsylvania in 1859, there was great celebration. Why was it so important? What did they want the oil for? The answer was as a fuel for oil lamps. The traditional fuel, whale oil, was in short supply and had become very expensive. A substitute needed to be found. The specification of the substitute was known. It had to be in liquid form at room temperature. It had to be volatile, so that its vapors would be easy to ignite. It had to be capable of rising up the wick of the lamp. It must burn with a clean flame, not too smoky. They knew that the replacement was to be found in crude oil, a compound called kerosene. But first, it had to be extracted from the oil. How could that be done? The method they used was distillation. Distillation of liquids was common in the 19th century. First, a liquid mixture is heated. As it boils, vapors are produced. When the vapors touch the cooler parts of the apparatus, which are at room temperature, they condense back into liquid. The temperature reading rises quickly to the boiling point of the liquid which is condensing. The vapors, these are what we're trying to isolate, can be passed through a Liebig condenser so that condensation takes place and the resultant liquid collected. It's only a part of the original liquid, so it's called a fraction. The kerosene produced by distillation of Pennsylvania oil made it an ideal lamp oil. State, liquid at room temperature, boiling point between 150 to 250 degrees Celsius, which makes it moderately volatile. Ignites easily at room temperature. Low viscosity, burns cleanly. With an ample supply of crude oil and using simple technology, kerosene became plentiful. As for the rest of the mixture, well, they didn't know what to do with it, so most of it they simply burnt off or dumped. 25 years later came an invention which would change the world and have enormous consequences for the growing oil refining industry. The invention was the internal combustion engine, which made the motor car a reality. A fuel was needed to drive the new engine. Kerosene was tried, but the mixture wouldn't ignite easily. It wasn't volatile enough. No, the specification was different from kerosene. State, liquid at room temperature. Boiling point, 30 to 80 degrees Celsius, which gives it high volatility. That makes for rapid evaporation, so ignition is easy. Viscosity, very low. Flame, clean. The answer was locked into the crude oil. But to get more out of that, they had to improve on the distillation process. This is a basic fractionating column. Using this, a mixture of liquids can be separated. When the mixture is heated, the vapors of the liquids boil off at different temperatures because they have different boiling points. The first stage of the process is when the vapors touch the glass tubes within the column and condense. The temperature there is 82 degrees Celsius. So far, it's simple distillation. The vapors are condensed by passing them through a Liebig condenser. The first fraction is collected. But in a fractionating column, other parts of the mixture continue to rise. Higher up at 67 degrees, another liquid condenses. It's a second fraction. A temperature gradient has been produced with a higher temperature at the bottom and a lower temperature at the top. The new product the early refiners obtained from fractionation was gasoline, which we know as petrol, and that technology is the basis of the oil refining industry today. The Shell Oil refinery at Stanlow in Cheshire is one of the largest in Britain. It can process over 35,000 tonnes of crude oil a day. Most of the oil to be processed at Stanlow is brought by tanker from the Brent oil field in the North Sea. The oil is pumped on shore, then sent by pipeline to the refinery 15 kilometres away. This is the main crude oil distillation unit at Stanlow. The heart of it is the fractionating column. At first sight, it bears little resemblance to the laboratory equipment we've seen. But strip away the pipes and the principle is the same. Crude oil is heated in a furnace to around 350 degrees Celsius and is pumped in close to the bottom of the column. At that point, it's a mixture of vapors and fine droplets. The vapors rise and some of the heavier droplets fall. Inside the column, there are trays where different fractions of the oil are collected. Each fraction is a liquid mixture with a narrow range of boiling points. Notice the temperature gradient. Different products are drawn off at different levels. Right at the top are the most volatile compounds, the light gases such as methane and butane, as used in hot air balloons. As the temperature gets higher, going down the column, the fractions are liquid. There's gasoline, which we know as petrol. Naphtha, an important chemical feedstock. Kerosene, which is now used as a fuel for planes. Gas oil or diesel. Getting heavier at higher temperatures further down, mineral oil to make lubricants. And at the bottom of the column, very thick liquids and solids such as wax, grease and bitumen, which have a very high boiling point. It's simple distillation, happening continuously at different levels. But why do all these different compounds separate? Crude oil is a complex mixture of gases, liquids and solids dissolved in those liquids. All the parts of the mixture are compounds of the elements hydrogen and carbon. They are called hydrocarbons. The simplest hydrocarbon is a gas, methane. On paper, its molecule is usually written like this, but in fact it's more like this, pyramid-shaped, a tetrahedron. A carbon atom always forms 4 bonds, and most commonly does so with atoms of hydrogen. Carbon atoms can also bond together end to end to form long chains with many atoms in them. The bond between any 2 carbon atoms is very strong. The length of the chain determines most of the physical properties, and here's the key to understanding how refining works. Compounds with short chains are gases or liquids that boil easily. They're very light and volatile. Compounds with medium-length chains boil at higher temperatures. They are low-viscosity liquids. Compounds with very long chains are solids. At Stanlow, the results of processing North Sea crude oil in the fractionating column are these. Calculating by weight, the light gases only make up 2% of the products. Gasoline is 15%. Naphtha is 10%. Kerosene, 15%. Gas oil, 25%. The rest, 33%, is the heavy residue such as bitumen. This is a typical split from the basic refining process. But at the beginning of the 20th century, it wasn't good enough. Within a few years of the introduction of the motor car, there just wasn't enough gasoline to keep up with the soaring demand. In the year 1900, there were fewer than 5,000 cars in the United States. By the outbreak of the First World War, there were more than 1.6 million. Oil refineries were producing too little gasoline and too much of the heavier fractions such as gas oil. Could that balance be changed? And if so, how? A new technique had to be devised. Here, a fraction of oil absorbed in glass wool is being warmed. The heat causes vapors to be produced. They pass over a hot catalyst, which allows a reaction to happen faster and at a lower temperature. The catalyst is simply broken porcelain, which provides a surface where a reaction can take place. There are two products from the reaction. The first is a clear liquid, which distills into a collecting tube. The second product is a gas, which is collected over water. So what has happened? Let's compare the original fraction with the distillate. The original fraction is quite viscous. The distillate is not. If a lighted taper is applied, they react quite differently. The original fraction does not ignite when a flame is near. But the distillate ignites very easily. It's much more volatile than the original, which suggests that it's a lighter fraction. Let's compare specifications. The original input, gas oil, has a boiling point of around 300 degrees Celsius. It will not burn and has high viscosity. The distillate output material has a lower boiling point of 50 degrees Celsius. It ignites easily and has low viscosity. The distillate matches the specification of the essential component of crude oil, gasoline. What has happened? In fact, when the long chain molecules in the fraction are subjected to high temperature in the presence of a catalyst, they break up into shorter chain compounds. The process is known as catalytic cracking. Today, catalytic cracking is as important commercially as the initial refining. It's carried out on a massive scale at Stanlow. This is the biggest cat cracker in Europe. The heavy fractions from distillation, the compounds with the long chain molecules, are the feedstock for this process. The fractions are heated and combined with a hot catalyst. In this case, it's aluminium oxide. The mixture is fed into the reactor. Heat is crucial. In the reactor, the temperature is 490 degrees Celsius. This level of energy is required to break the strong bond between the carbon atoms. The vapors from the reactor then pass to another fractionating column for further separation. During the reaction, the catalyst absorbs some of the hydrocarbon gases and it becomes coated with carbon. Steam is used to remove the hydrocarbons so that the catalyst can be put through the cracker again. It goes into the regenerator for cleaning and recycling. Catalytic cracking significantly alters the balance of the products from North Sea oil refining. The percentage of gasoline has more than doubled to 32%. And there's a new group of products altogether, alkenes. Where have they come from? Let's go back to our cracking experiment. Remember the gas that was produced? We're going to test it with bromine water, which decolorizes in the presence of alkenes. If we shake the original liquid with bromine water, there is no change in color. If we put the bromine water into the tube containing the gas, the solution loses its color. So, what does that tell us? The cracking process seems to release some compounds which are not even found in the original crude oil. What happens is this. When heat is applied to a chain with, for instance, 10 carbon atoms, it splits to form a shorter chain with 8 carbons and a new compound which has 2 carbons but only 4 hydrogen atoms. In order to form 4 bonds, the carbon atoms are joined by a double bond, which changes the properties of the substance considerably. The new substance is a gas, ethene. But once again, when it was first produced, there was no use for it, so it was burnt off. But all that changed by accident in 1932. A series of experiments on chemical reactions under very high pressure was being conducted at ICI in Cheshire. One of the reactants was ethene. As notes from the time reveal, the equipment in fact leaked and a waxy solid formed in the vessel. It was the first glimpse of polythene. What had happened? The reaction involved is almost the reverse of cracking. This time, lots of hydrocarbon molecules will join to form a new compound. One of the two double bonds in the ethene molecule breaks, leaving a single bond. This enables molecules of ethene to join together end to end to form a very long molecule of polyethene, or polythene. The process is called polymerization, and a whole new industry has grown from that discovery. At the Shell Chemicals plant near Manchester, ethene from oil begins the polymerization process as a gas. It's fed into a pressure chamber, where it's compressed to 3,000 atmospheres or bars. Steam is used to heat the gas to 170 degrees Celsius, and oxygen is added to initiate the polymerization reaction. The molecules of ethene come together to form the new substance, polyethene. The liquid polyethene is extruded and sliced into tiny granules called nibs. The nibs are the end product for this plant. But some are tested in the laboratory on site. The nibs are fed into a reactor and heated, which causes them to melt and fuse together. The thick liquid polythene is then stretched out and air is blown in to form a continuous tube. The purpose of the test is to ensure that the polythene nibs meet the correct specifications for the industries that will be using them. The product here is polythene bags. Polymerization is just one of the many ways to make use of the products of refining oil. It's a multi-million-pound, multinational business and fiercely competitive. But every column and every pipe of this refinery is controlled by a sophisticated computer program. The computer is fed with data on the latest prices of raw materials and end products. It then works out how to make the biggest profits and tells the refinery how to do it. Simple as that. Just about everything that we can get from the original refining of crude oil is made use of. There's only one problem. The oil will eventually run out. So what's going to take its place? Very expensive. A substitute needed to be found. The specification of the substitute was known. It had to be in liquid form at room temperature. It had to be volatile, so that its vapors would be easy to ignite. It had to be capable of rising up the wick of the lamp. It must burn with 1,001 items in the home, office and industry. How do so many things come from one rather unpleasant and smelly liquid? That's a difficult question, but it happens here. In this industrial complex, crude oil is broken down into its constituent parts, dozens of products from a single raw material. What do these things have in... It wasn't always like this. When the world's first oil well spouted black gold in Pennsylvania in 1859, there was great celebration. Why was it so important? What did they want the oil for? The answer was as a fuel for oil lamps. The traditional fuel, whale oil, was in short supply and had become common. The answer is this. It's hard to imagine that thick, black crude oil is the source of so many familiar things. Not just fuel and oils for cars, planes and ships, but plastics, fibers, detergents, a